privilege of working with some really outstanding people, and they deserve a lot of the credit for this work. Matveyev, a student, Tsai, a student at Stony Brook, Martin Rocek, my colleague at Stony Brook, Zhang Shuchuan, who will be talking here, Professor Norman Biggs, F.Y. Wu at Northeastern, and two people who are here, Jesus Salas and Jesper Jacobsen, or Jesper Jacobsen, depending on how you pronounce it. Outline of my talk is here, and I apologize in advance. I do show too many transparencies, but I guess the point is that I don't have the chance to meet a lot of mathematicians very often, and so my technique is to give you a glimpse of the kind of stuff I do, and then, you know, in informal discussions we can pursue further analysis. If I were talking to physics, you know, when I teach statistical physics or something, of course I go slower, but anyway.
I thought you were going to say for physicists you go faster.
Yeah, well, you're right. Probably I should have said that. Yeah. Anyway, some StatMech background. I'll talk about zeros of the partition function. StatMech is functions of temperature and magnetic field. These are called, respectively, Fisher and Yang-Lee zeros, or Liang zeros. They're accumulation sets B and studies for Ising of Potts model. The zeros of the general Ising model, by which I mean we put on a magnetic field. That's generally not been discussed here, except some very eloquent discussions by Alan about the Yang-Lee zeros and that program with both temperature and field complexifying. I'll then talk about zeros of chromatic polynomials, which are, of course, as you know, temperature is 0, Potts antiferromagnets. My apologies, the Xerox at Stony Brook is not the greatest, and it has a middle point here where it messes up. But anyway, antiferromagnet and the resultant be in the Q-plane for these graphs, recursive families of graphs. Then I'll go on to zeros and the accumulation set B of Potts or Tutte polynomial in the Q-plane for arbitrary V or temperature, and in the V-plane for arbitrary Q. So this is going to be a theme throughout the talk. And just to emphasize to mathematicians, in some sense, we are interested in a 3 complex dimensional manifold here. A hypersurface in a 3 complex dimensional manifold. Magnetic field, and is this thing working? Yeah. Magnetic field, the temperature variable, and the Q variable. So we're taking slices usually, and but the real entity itself has tremendously interesting complexity. Okay, so then zeros and B of as we say, in the Q plane for arbitrary V, in the V plane for arbitrary Q. Throughout, I will mention open problems. I also submitted a sort of physicist ideas of some open problems for the problem session and conclusions. We've also done similar things on other polynomials that are special cases of Tutte, including flow and reliability polynomials and percolation. I'll not cover these here. Some of them will be in the talk by Zhang Shuchuan. Okay. Some StatMech background. I can be pretty quick here because Alan gave a beautiful talk, series last week, and his talk on Monday, and other speakers have covered a lot of these concepts. So please, I hope that most of you were there, so I'll go pretty quickly. Okay. An important function in StatMech and condensed matter physics is the partition function Z. This function enters, for example, in the study of liquid gas and magnetic transitions. Physicists are often interested in properties of many-body systems and cooperative phenomena on loopless graphs, G, the usual notation, which are regular lattice graphs with some boundary conditions. The physicists tend to call vertices sites and edges bonds. Let's consider a system with dynamical variables sigma I, classical spins defined at each vertex vi and the vertex at v, taking on some set of discrete values. In thermal equilibrium, and by the way, a big subject in physics is non-equilibrium thermodynamics. Well, so we're taking a special case here very much. But anyway, thermal equilibrium, there exists a temperature T. Beta will be 1 over kt, k is a Boltzmann constant. This is the partition function. The Hamiltonian H will involve interactions between spins on adjacent vertices and a possible external magnetic field. The Ising model or Ising model has been defined many times. This is my notation. Here's the spin-spin exchange constant, the magnetic field, Eij is the edge connecting these two vertices. J greater than 0 is favoring ferromagnetic, that is to say parallel alignment of the spins. J less than 0 favors anti-parallel alignment. It's convenient to define dimensionless variables, k, which is beta j, just because they always occur in that combination, and little h, which is beta h, again, because that always occurs in that combination. So z is summation over spin configurations of this exponent, k times this interaction term, h times the single site term. We'll define n to be the cardinality of v. The free energy, the real free energy, with dimensions of energy is this. It's more convenient for our purposes to deal with a reduced dimensionless function f, which is limit n goes to infinity, n inverse central log z. There have been a number of very rigorous discussions by various people on, the conditions under which that's well defined. Z Ising and F Ising are invariant under simultaneous replacements. H goes to minus h, and hence inversion of mu. Mu is equal to e to the minus 2h. For a finite g, then finite graph g, zi is a finite Laurent polynomial in something I'll call a, which is e to the 2k, or z inverse, and in mu. By the way, later on, when we go to Potts notation, there will be a factor of 2 rescaling here. It is therefore determined by its set of zeros in z for fixed mu, or in mu for fixed z. The generalized model, what I'll refer to, it has a non-zero h. This is just a definition of the thermodynamic limit. It's been defined before. Consider a regular lattice graph forming a d-dimensional lattice of size L1 through LD. Definition, the thermodynamic limit is a limit where each of these links goes to infinity such that the aspect ratios, in other words, just these ratios of different links, is c, where c is some finite constant not equal to 0 or infinity. We will, in fact, also consider infinite length limits of finite width strips where the aspect ratio is 0. Those turn out to be interesting for a number of reasons. Derivatives of z, as a number of speakers have noted, yield precise thermodynamic quantities. For example, first derivative with respect to beta is the internal energy. Second derivative is specific heat. The first derivative with respect to h at h equal to 0 is the spontaneous magnetization. Second derivative of f with respect to h is the initial susceptibility if you set h equal to 0. Physically, the Ising model or Ising model gives an approximate description of a uniaxial magnet, a liquid-gas transition via the lattice gas formulation we've heard some things about in previous discussions, and also order-disorder transitions in binary alloys. If you know what beta brass is, for example, that's a famous example. Exact solutions are known for one dimension, and if zero magnetic field is true, then in 2 dimensions. That was done by Onsager. If h is 0, then this is invariant under the symmetry group Z2. And for this h equals 0 case, and dimensionality above the lower critical dimensionality on integers d, in the thermodynamic limit, greater than or equal, the model has a continuous or second-order phase transition at a certain critical temperature, Tc, equivalently Kc or Zc, between a Z2 symmetric high-energy phase, we call it paramagnetic, and it has 0 magnetization, and a low-temperature phase in which there's spontaneous symmetry breaking of Z2 with the onset of long-range ferromagnetic order. If J is greater than 0, if it's less than 0, there may be anti-ferromagnetic order. There are singularities in the free energy associated with this, and also in thermodynamic functions derived from the free energy. For example, specific heat, the susceptibility, and the magnetization. These define critical exponents. By the way, just because many of you are English or Australian, you should know that some of the very early classic work on series expansions and analyses of these singularities was done by people like Dahm, Sykes, Rushbrook, Fisher when he was here, Gaunt, Gutmann, etc. in King's College. So there's a tremendously strong English tradition, well, I should say, Commonwealth tradition of work on singularities at second-order phase transitions. Okay, on a kappa regular graph, G with even coordination number, physicists call this coordination number, the vertex degree. Ising model is a Laurent polynomial in the square of Z, e to the minus 4k, as well as mu. If h is equal to 0 and the graph is bipartite, then there's a trivial isomorphism that takes k to minus k, and then thereby implies that z is symmetric under inversion of this little z, which just interchanges these phases. These are some things you might care to remember later for some graphs. For the square lattice, the critical point for the PM-FM phase transition is given here by 0.17. For the PM-AFM transition, by that symmetry, it's just the inverse of that, which is this, about 5.7 or so. So there are three physical phases: paramagnetic in this interval, ferromagnetic 0 to here, AFM from there all the way out to infinity. Okay, definition of Potts model. This has been done many times also. We have a graph G. For our purposes, we can take it to be loopless. Vertex at E, edge set E, the edge set E. We have several of these variables now. They can take on values 1 to q. Here's our partition function. Here's our interaction. This is our Konecker delta. For q equals 2, this is equivalent to Ising after rescaling k by a factor of 2. And this is of considerable interest to physicists, and especially, I mean, you go way back, even the late 70s, early 80s, this was heavily studied. And why was it of interest? Because it provided another set of what we call universality classes, or types of critical phenomena, which were different than Ising. And I should mention for q equals 3 and q equals 4. When you go above that, you get a first order transition. Q equals 1 is also interesting for percolation. Using this identity, which has been discussed a number of times, with v equals e to the k minus 1, you can recast this in the Castellane Fortuin, and I'm mispronouncing the Dutch, sorry about that, cluster formula shown here, which is this beautiful formula that replaces a sum over spin configurations by a sum over spanning subgraphs, where spanning subgraph means a vertex set is the same edge set as a subset. Okay, and this allows you to generalize Q from non-negative integers, which you really needed for the Hamiltonian formulation, to positive real and indeed complex numbers. It also makes it clear that this is a polynomial in Q and V. Okay, and again, going quickly still over some of these things that have been covered by previous speakers, but some of you might not have been here. The Tutte polynomial, or Tutte-Whitney polynomial, is defined in this way. Sum over, again, these spanning subgraphs. K is the components of G prime minus K of G. This is also related to a rank. And y minus 1 raised to the power of the cycles, independent cycles on G prime. This is, again, obviously a polynomial in x and y. A very interesting property that ties these together is that with this transformation of variables from x to qv, y to v, and the inverse is a hyperbola in the xy plane, which fixes q, one has this equivalence between the Potts model partition function and the Tutte or Tutte-Whitney polynomial. You've all seen the definition of chromatic polynomial as a special case of the Tutte polynomial. I would say, you know, echoing what Alan often says, that this is an example where a physics point of view is really makes it obvious. Namely, for the antiferromagnetic Potts model, as t goes to 0, k goes to minus infinity, okay, so that, or v goes to minus 1, so that only spin configurations, the only ones that contribute are those for which adjacent spins have different values. So of course, then, obviously, this is the chromatic polynomial. Other special cases, including flow, reliability, polynomials, Jones polynomials, valuations include things like spanning trees, spanning forests, etc. As we've heard, there were pioneering studies going back all the way to 1912 by Birkhoff and Lewis, all the way, 1946, their work, etc. Whitney, Tutte, Reed, Norman Biggs, and various other people. There are, in case you don't know the physics literature too well, there are two very nice reviews by Baxter and F.Y. Wu. Well, this is a Welsh type diagram, and I can't go into details, but you know this as well as I do, I'm sure, that there are just loads of interesting special cases here. Ferromagnetic Potts models on these hyperbolae here, Jones polynomial here, the chromatic polynomial here at 0 temperature, chromatic polynomial at finite temperature on this strip here from y equals 0 to y equals a, complex temperature generalizations thereof, the flow polynomial, etc. I first saw this in a very nice book by Welsh, so Sorry?
Put this thing over
Yeah,
there.
in fact, that's going to get used very shortly. But yeah, sure, I'll put this over here. And if the reference to that, if you want to see, is Welsh's book on a very nice book from which I learned a lot. I'm sure other people did also. Okay, zeros are the Ising model partition function. As Alan has described in the workshop last week and also in his talk, just as in mathematics, one gains a deeper understanding of functions of a real variable by going to complex variables. So also, it's useful to generalize k, or equivalently z, little z, and h, or equivalently mu, to complex values. The generalization for mu, which is related to the fugacity in a liquid-gas transition, it was made by Yang and Li, or Li and Yang, in 1952. The generalization complex z by Michael Fisher in 1965. And of course, this is necessary if you're going to look at the general set of zeros of the partition function. So many people have discussed BK Braha, Kahan, Y. So I'm going to give you a very short, kind of very elementary illustration of that. Consider a simple example showing the role of zeros in Z and how they accumulate. So consider an Ising model on a lattice strip, length Lx, I'll call it M, finite width Ly. Okay, so we have that. Let's put on periodic longitudinal free transverse boundary conditions. We'll define a transfer matrix. Here's the matrix element. And again, my Xerox at Stony Brook is not the greatest, but anyway. Z is trace of t to the m here, and that's a sum of the eigenvalues of that transfer matrix. Therefore, when we take n to infinity and we take the 1 over n, here's m, or 1 over n power, to get the free energy, it just picks out the one of maximal magnitude, so we get this.
I'm confused between M and...
Yeah, sorry. I'm using m because I'll be doing strips, and the strip length is m. N refers indeed to the total number of vertices, okay? So when you have the total number of vertices, then n, of course, is...
N is Lx, Ly.
Exactly. So then the 1 over nth power brings down a 1 over L sub y. Yeah, sure. It's just a straightforward thing. Okay. So where L max, Lj max, is the lambda of maximal magnitude. As one varies z, this temperature Boltzmann parameter, for fixed mu or mu for fixed z, one can cross a boundary at which there's a switching of dominant eigenvalues with a resultant non-analytic change in f. This boundary locus, that's why I call it B for boundary, is non-analytic. At that locus, f is non-analytic and is defined, in fact, by the solution to the equation of degeneracy and magnitude of maximal eigenvalues. For many cases, this is comprised of curves and possible line segments. So let's take a really simple example, because I want to show also how this relates to integral representations. Consider the case where two eigenvalues of this transfer matrix give the main contribution. So we have that. Clearly, the zeros occur where the magnitudes are the same. And so this shows, if I can make this thing, shows that as n goes to infinity, they generically accumulate and merge to form a locus B, which is just the solution of that equation. There may also be isolated zeros. General mathematical theorem, as we've heard, was due to Braha, Kahan, and Weiss in this period, mainly applied to chromatic zeros, but it's general, and they knew it was general. For finite n, we can, for technical convenience, write this as this product and break it into two symmetric parts, and then combine these to get a cosine here. Letting n go to infinity, we get an integral representation of this, and this is essentially a free energy then. Integral d theta over 2 pi times this logarithm. And this is the logarithm of the maximal eigenvalue between these two, as you can verify by doing the integral. On a finite graph, of course, G has no zeros on the physical real positive 0 mu axis, since it's just a, it's a polynomial with positive coefficients. However, in the thermodynamic limit, in fact, Alex Scott was mentioning the same thing in his talk today. For physical z and mu, you can have these zeros come down and pinch the physical axes. And these are associated with physical phase transitions as these curves cross the axis. So that's a connection. Alan made the same point very eloquently in his talks last week and on Monday. Okay, because expressions for z and in the thermodynamic limit f for h equal to 0 on two-dimensional lattices, again for Ising, are known, the complex phase boundaries can be worked out in a straightforward way. For example, in Fisher's conference paper, he actually never wrote, he never pursued this, because when he just a year or so later, he went on to renormalization group, and he considered that to be a very powerful way of analyzing phase transition. So he didn't really pursue this much, but it's come back, rising from the dead or so. Anyway, the Fisher circles are shown here. And in the A plane, A in terms of Potts variables is going to be related to V. Okay, so for the square lattice Ising model, this is the form of the reduced free energy. It's shown here, where P is cos theta 1 plus cos theta 2. The circles then, the Fisher circles, are the locus of solutions to the condition that the argument of the log in the integrand is 0. The zeta minus C, and I guess I should show my first picture over here. So these are the Fisher circles, and I have to make sure this doesn't slip down. Okay, so these are the Fisher circles in the z-plane, and this is invariant under, because it's a bipartite lattice, and if I can make this thing, yeah, z goes to 1 over z, so you readily see that's inversion symmetric. It's also, of course, symmetric under negation, the reason being that it's a lattice with even coordination numbers, so it's really, the partition function is really a Laurent polynomial in U. And that's obvious here, by the way, because although z appears, notice that p is cos theta 1 plus cos theta 2. So under that range of integration, you flip the sign of p, and you show that this is, although it's ostensibly dependent on z, it's really z squared. Okay, it's invariant under z goes to minus z. So this is naturally then recast in a different complex plane, namely the U plane. In the U plane, this has the form of a limaçon of Pascal. It's shown here. These are the equations of the curve. There's a multiple point here, and I want to just make the point, which I'll make shortly, but I'll make it here. Okay, that the physical ferromagnetic, I keep trying to, yeah, the physical ferromagnetic phases. So this tiny little red interval here between 0 and 3 minus 2 square roots of 2. The paramagnetic, where the Z2 symmetry is symmetric, is here. The antiferromagnetic, again, remember the U to 1 over U symmetry, is just the flip of that. It's this, around 5.73 plus 2 square roots of 2. Now the key point is that you can extend these real physical intervals to the complex plane. CE means complex extension. You can extend this and the associated thermodynamic functions all throughout this space between the outer and inner loops of the limaçon, and similarly for functions out here and in here. Henceforth, I'll drop this CE for complex extension. Okay, going back to here, well, I say the same thing. These are the equations for the limaçon, the inner loop, the outer loop, which physical phases they include, and which extensions, complex extensions of those physical phases they include. Notice that this example shows, I think, nicely the connection between graph theory. That's what we started with. We took a thermodynamic limit, getting us really out of discrete mathematics into complex analysis, looked at zeros of z. They, of course, merge along these boundaries. Okay, that's Fisher's point in what he was doing here. And they also get you into algebraic geometry. Okay, the thermodynamic functions, as I mentioned, can be analytically continued. This is a classic calculation, a tour de force by Young in 1952 of the magnetization, shown here. In terms of the U variable, it's shown here. All the physicists will recognize that this is the physical critical point with the famous beta equals 1/8 exponent. This beta is not 1 over temperature. Sorry about that. In the ferromagnetic phase, this tiny little red interval, but you can analytically extend this all throughout that inner loop of the limaçon. For example, it has a 0 where it vanishes with a different exponent at 1/4 at this intersection point U. Remember, U is plus or minus I as far as the Fisher circles are concerned. Besides the h equals 0 case, the partition function and free energy are known for the 2D Ising model. For this non-physical case, h equals, remember, little h, so beta times capital H equals I pi over 2, or in other words, mu equals minus 1. Remember, h equals 0 is mu equals 1. This was discovered by Yang and Lee. Further work was done by McCoy and Wu. And the phase diagram for that, we worked out a straightforward exercise to do that. And what you find is a result, which is, oops, my transparencies. Anyway, I'll just state it in words and show you later. It's the unit circle in the U-plane union with, so this unit circle in the U-plane union with a finite line segment on the negative real axis from about minus 0.17 to about minus 5.7 or something. Okay? And in fact, one can also look, so what have we done so far? We looked at zeros in complex temperature for fixed h or equivalently mu. We can do the opposite. We can look at zeros of z in the mu plane for fixed temperature, or z. And you have heard a number of times of the famous work of Yang and Lee in 1952, who showed that the zeros of z in the mu plane lie on a unit circle, mu equals 1, and for ferromagnetic coupling. This is not true for anti-ferromagnetic couplings, by the way. And this, of course, then, since mu is e to the minus 2h, this corresponds to pure imaginary h. As n goes to infinity, these zeros merge to form a locus b mu, comprised of part of a circular arc with endpoints at certain values of theta. They pass through mu equals minus 1 or theta equals pi. In fact, they degenerate to that point at k equals 0 or beta equals infinity, t equals infinity. Beta equals 0, t equals infinity. Yeah. And as we decrease the temperature, the arc grows toward the right. So T3, T2 going down to Tc is a decreasing range of sequence of T. And you see how it enlarges. In the limit, T goes down to Tc. It pinches the real axis. And thereafter, it's a closed circle. Okay, so that's the famous Yang-Lee circle theorem. Actually, one of Allen's early and very beautiful papers with Elliott Lieb was the generalization of the Yang-Lee theorem. And there's been a lot of interest in that over the years. Okay, so now let's say a few words about complex temperature zeros of the Ising model for h not equal to 0. Okay, so now this is not a known case in general, except for those two cases I mentioned, h equals 0 and I pi over 2. There is no known closed form for the Ising model on a lattice with d greater than or equal to 2 for arbitrary non-zero h. This is an open problem, and of course, knowing something about the zeros is of interest. Because of this k to minus k symmetry, or I'm sorry, h to minus h symmetry, or equivalently mu to 1 over mu symmetry, with no loss of generality, we restrict to the interior and rim of the unit disk. Well, a number of years ago with a student in Matveyev, I studied this, and we generated a number of results. I'll show maybe one or two quickly. As you turn on a real h, you find that the inner branch of the Limaçon breaks. And there's actually, for physicists, there's a Leibowitz-Penrose theorem that guarantees that that will be true. So you see the outer circle, if you in the thermodynamic limit, this is closed, but the inner one breaks into these prongs, and they retract from the real axis. The inference for the thermodynamic limit is shown, and I better put these over here, is shown here. Okay, so as I say, the study of these zeros is a non-trivial extension of what's known. And if I could, yeah. So what do we know? Well, we know that the outer boundary certainly does continue to go around that red boundary, separating this interior part from the outer part. Proof you assume the contrary, then you could analytically continue the uniform magnetization from the antiferromagnetic phase, where it's vanishing identically, to the ferromagnetic phase, where it's non-zero. So this is closed. These are the prongs. What happens here, we don't know. That's still a subject of research. Okay, so that was a study we did going on the real axis between the exactly solved cases mu equals 1 and mu equals minus 1. We have recently extended that a bit to look, oh, and I just want to say something else. Yeah, a theme, one of the themes of this talk is going to be that you can learn interesting things from infinite length, finite width strips. And this is an example of that. This is an exact result. It's straightforward to get this. On the zeros of Z and the accumulation set for an Ising model on a Ly equals 2 strip with a square lattice, toroidal boundary conditions with a certain non-zero value of H. And you see indeed breaking of these prongs that were connected before. Okay, and these are branch cut singularities. These occur in with certain zeros of discriminants that occur in the eigenvalues. In fact, Norma Biggs will have a lot more to say about that later. The triple points, we also see a triple point here. If I can get this little thing to, yeah, triple point. And that, again, is easy to understand from the point of view of what are the dominant eigenvalues. This was another paper we did on a clock model, Z6 clock model, but it illustrates the same thing. Here's the B there in the complex temperature plane. And how is that B arising? Well, we can see how it's arising by looking at equimodular curves, which are solutions of degeneracies of leading eigenvalues. So here we come along here. We hit this point where these are no longer the leading eigenvalues. Now, these two are the leading eigenvalues. So you go up along here. That curve itself continues smoothly. But in this region, those are subleading, so they don't determine the actual phase boundaries. And then we come down here, and there's another switch here, and so forth. So the triple points have, in some sense, straightforward understandings in terms of dominance of various eigenvalues and how they switch. Okay, so in 96, we looked at real H. And one should say, just apropos of the issue of how much you learn from infinite length, finite width strips. We know that the free energy is analytic for these strips. It's easy. You take the proof is you consider the transfer matrix. It's positive. It contains positive entries. You apply the Perrin-Frobenius theorem. That yields a unique maximal eigenvalue. So for physical temperature, nothing funny happens, nothing non-analytic. But for complex temperature, things can happen. So I illustrated that with a few cases. Okay, so for the H equal to 0 case, one can illustrate that again. I won't show you all the illustrations. They'll be in, oh, by the way, I'll skip some transparencies because I have too many, but they will be in the compendium that's on the net that you can look at. Okay, and I keep having trouble with this button. Yeah. And so one can envision a certain heuristic procedure for relating phase boundaries for these infinite length, finite width strips to what happens in the thermodynamic limit. So let me illustrate that, because this is something where maybe somebody could make some real progress. Okay, so this is a more or less trivial, it's an easy, straightforward solution of the Ising model on infinite length finite strip. And we see this boundary, the fact that it passes through u equals 0 is simply the 0 temperature critical point. But notice something important. If I go back to my limaçon here, okay, and I imagine a heuristic procedure. So I take this, I imagine that's a rubber band. I just pull it out. But notice there's a u to 1 over u symmetry. The minute I pull this out, these things that go off to infinity get pulled in. What do I produce? Topologically, and this goes through u equals 1. So topologically, I exactly reproduce, by a essentially trivial calculation, the qualitative features of the phase diagram of a highly non-trivial, this is the Onsager solution in 2 dimensions, okay? So this should teach you that exact solutions on infinite length finite width strips can, in some respects, teach you interesting things about 2 dimensions, okay? And going back to our work with this magnetization then, the next thing we did was to take another natural path connecting the 2 exactly solved cases, mu equals 1 and minus 1. One's to go along the real axis. Remember, with no loss of generality, we're in the unit disk. The other is to go along the rim of the unit disk. And we've done that recently. Just you may wonder, why did we wait 10 years? Yeah, we wonder that too. Anyway, we could have done it in 96. Anyway, it's an interesting calculation. And so we can study that. What are the complex U zeros for non-zero, not just real H, but also H on the Yang-Lee circle, okay? So on that semicircle. Actually, with no loss of generality, you can stick to a semicircle. So we have this, okay? So now, again, the real answer is not known. This is an open problem. And we have mapped out these zeros in the complex temperature plane as we vary mu along the Yang-Lee circle. Or to say it differently, we're varying theta from 0, that's exactly known, that's h equals 0, all the way over to theta equals pi, which is the other one. We see the outer branch of the Lie muscle coming in. The inner branch moves in a complicated way. This is very complicated. We don't really know what's going on here. We see the development of this interval on the negative real axis. And we get a very interesting thing here, which is that, and by the way, just to say, in the thermodynamic limit, it's easy to prove that these are closed, okay? And we find an interval here on the real axis, which, as I say here, has the very interesting feature that this real line segment extends through part of the physical ferromagnetic interval with a right-hand endpoint at the same temperature at which the Yang-Lee, physics calls the edge singularity. You can think of it as just the endpoint of that circular arc, occurs at mu equals theta equals I pi over 2. Okay, so that's an illustration of one of these three complex variables. We have temperature, we have Q, and we have H. And we're looking at a certain subset of that. We've done some of this on very large, well, for us it's very large lattices. It's a huge calculation. And this is what we get for the most symmetric case, theta equals pi over 2, or in other words, mu equals I. And this endpoint here ends at 0.8. So as I say, there's much more to be done here. And many of the discussions here have concentrated on complex Q for things like chromatic polynomials or float polynomials, complex P for reliability polynomials. So part of my message is there's some other interesting complex variables too. Alan made the same point with the Yang-Lee theorem, okay? And so mathematicians may get interested in that, okay? Other slices of this hypersurface in three complex variables, okay? But sometimes you feel like this blind person looking at an elephant, right? 19 blind people look at the elephant, which is this hypersurface, and they see all sorts of different things of the elephant. If only you could see the elephant itself, right? But we can't right now. A little bit more on the idea of getting from infinite length finite width strips to see things about the thermodynamic limit in 2 dimensions. Going back to the Fisher circles, well, you know what they look like, just those 2 Fisher circles. How well can you understand that from infinite length finite width strips? So we did this. This is a calculation we did, a cyclic strip. I guess it was a paper I wrote around 99 or so. And again, we have these invariances here. And we have this. This is, of course, an artifact, quasi-one-dimensional artifact, 0 temperature critical point. But notice what I can do. Imagine again that I think of these as, you know, Thurston might think of them or something in topology. I take these curves, I pull them apart, okay? And once I do that, the inner curve, immediately the curves that go to infinity come in, okay? So notice that when I do that, I have completely reproduced the topology of the famous Fisher circles, okay? Because, among other things, the intersection point here is at I. Is it at z equal I and minus I? So if in fact, let me actually put this on here. It's not the same scale, but you can see what I mean. These will come around, form circles. These will form circles. Well, how much better do I do by going to larger lattices? In some sense, I do worse, okay, because the one-dimensional artifacts get worse. Namely, we did this for a width 2 strip, okay, shown here. There are more curves. There actually, one could generalize this. There are 6 branches of 3 curves going through the origin. There's a lot of junk here. So now we have to pull those out from the middle. We move those over to make the circles, and somehow we get rid of all this clutter here. So actually the message is sometimes it's even best to work on the minimal length strips. I won't show it. You can do the same thing for the triangular lattice. Okay, so now we get, of course, we know what the Ising model looks like for 0 field. What about for, and we've studied this for finite h. Now we go back to h equals 0, and we go back to the Potts model. Okay? And so this is, aside from the Ising special case, q equals 2, this is almost virgin territory. Okay? There are some things that are known. We've had this defined before. A is e to the k, v is e to the k minus 1. Zeta is this nice duality variable here. Under duality, it just inverts. And we know, for example, on the square lattice, also triangular honeycomb, the value of the critical point. So that's fine. But do we know the complex temperature phase diagram? No, we don't. So in old work, we've studied this. The model has a PM to FM transition for q equals 3. This is the FM to PM to FM transition, and the AFM transition is driven to t equals 0. Okay, and which is that it's critical at t equals 0. That's a result due to Lieb and Lenard. So we infer that the boundary will travel through that point. Okay, which in these variables is VC is square root of 3, and at v equals minus 1. There will be a dual of this, okay? And I'll show you a plot of that right now. This is an old many people have done these calculations. This is what it looks like. So this is and again, in the thermodynamic limit, if I can make, this circle closes, and it's very pretty. This is just the z equals 1 circle, or in these variables, a minus 1 square root of 3. What happens over here? There's a lot of scatter of zeros. And you can see this problem, I can tell you, has been around for 20 years. Okay, so it's not an easy problem. We know certain things about this. From a low temperature series expansion and analysis of that, we determined exact values of some complex temperature singularities. We also can sort of see that there might be some kind of regular behavior there. So we can play the same game, but we calibrated that on the Ising model. Now let's use it for a case where we don't know the answer. So here's a calculation that we did on the complex temperature zeros of q equals 3 Potts model, L equals 3 strip here in this paper, and we get these curves. So what can we make of these? Well, we see, it's not quite the same scale, sorry, but we see pretty good, and again, we bring these in from infinity because we know that's a one-dimensional artifact. So we get that circle pretty well. We really want to see what's happening over here. Unfortunately, this is a mess. I mean, it's not this kind of mess. It's a different kind of mess, okay? The curves are rather complicated. And so it's somewhat challenging to infer what we would like to do on this, okay? For example, here, you would like to test this kind of ansatz. So let me explain that. The zeta equals 1 circle is this, okay? And maybe that continues all the way around. We know from this Lieb-Lenard result that we go through a equals 0, the dual of that. Therefore, we know this boundary goes through a equals minus 2. There's an old, and I have some, sorry about that. There's an old conjecture based on some work of Baxter originally, but the conjecture is due to Maillard and Hamal. This is a conjecture that there's another circle. A plus 1 is square root of 4 minus q, which in this case is just 1. Okay, so that's this circle. And this is the well-established circle. Well, how well does that fit the data? Well, it's not clear. In particular, it is not the answer, the full answer, because it does not have these singularities that we know are there from series expansions. So that's the kind of game that one is trying to play. I should say that we've also done some work on self-dual square lattices, which have some very nice features. For example, in the zeta plane, v over square root of q, we see, again, an arc of a circle. It does go through these points exactly. And so in that sense, it reproduces features of the two-dimensional thermodynamic limit that you would like to see reproduced, which it shows that a number of these features can be exactly reproduced by infinite length, finite width strips. Okay, and I guess I said everything on that transparency. And on this transparency, I've shown you this plot of zeros in the A plane, and I have shown you this the nice features of what happens when you go to self-dual variables. However, I emphasize it remains a challenge to use exact calculations of these loci to get information about these complex temperature zeros. Okay, now I'm going to switch gears completely. We'll go to the other slice of this hypersurface in three complex variables, namely zeros of chromatic polynomials. And I'm going to go fast here because this has been discussed by a lot of people. We know what this is. Recursive graphs, we know what they are. I think it was Norman Biggs who emphasized this rigorous definition. First of all, the W function is p to the 1 over n in the n goes to infinity limit. It's related to the entropy by S is k log W, the famous Boltzmann formula. The motivations for this, there are many from the point of view of a physicist. Non-zero ground state entropy is of great interest. It's actually a violation of the third law of thermodynamics. The third law of thermodynamics says that the entropy per site has to go to 0. Well, it doesn't always, okay? It's not really a law. The Potts antiferromagnet is a nice model exhibiting ground state entropy. I'll show that later. And we've already discussed these very beautiful connections with mathematics. And last but not least, there's a physical example, which is ice. And since part of my job here is to do a little bit of physics for you, I want to teach you a little bit about that, but really quickly, okay? So ice is a hydrogen-bonded molecular crystal, which at 1 atmosphere has a wurtzite crystal structure. This is what it looks like. It's sort of like a diamond lattice, a tetragonal bonding, coordination number 4, or vertex degree 4. Here are the hydrogen, here are the oxygen molecules, red. The hydrogens are like this. The hydrogens are not equidistant on the bonds. So for each edge of this graph, there's a twofold possibility. But note that there's a constraint, namely the constraint of local electric neutrality. You can't have 3 hydrogens piled up on this oxygen. That would be disfavored, obviously, by the Coulombic energy. This has been a subject of great interest to physicists over many years. This goes back to a beautiful set of papers by Pauling, all the way by Linus Pauling, 1935. In the 60s, this was of interest in connection with ice vertex models. I'll get to that in a second, by people like Lieb, F.Y. Wu, Baxter. In fact, Wu has a nice review on this. It is indeed a violation of the third law of thermodynamics. This has been discussed by a lot of rigorous people, Griffiths, Eisenman, Lieb, Wu, etc. Specific exact calculations for the square lattice q equals 3 is Lieb. For the triangular, for q equals 4, Kagome q equals 3, that's Baxter. And Baxter has a paper which Alan and Jesus, and I guess Jesper, have maybe found some mistakes in, but in any case, this paper reports a W function for arbitrary q, which is a tour de force, really. Okay, so that's some of the background. The measured ground state entropy for ice is shown here. This is the molar entropy. If you calculate the exponent of that, which is the degeneracy, you get about 1.5. We know that from neutron diffraction experiments. And I don't have the time to go through it, but Pauling gave a beautiful estimate in which he decoupled that constraint. On each edge, there are 2 choices. There's a constraint of local electric neutrality. He put that on for general vertex. Well, I'm showing it for general vertex degree delta, but he, of course, did it for 4. And what he got was W equals 1.5 in agreement with the data. Very nice approximate calculation. Another kind of approximation, which started an entire field, is known as square ice. So that vert-side lattice has coordination number 4. So a natural sort of thing to do is, how about square ice? It has the same coordination number. So you can do that. You assign arrows. These are these dipole moments associated with the hydrogen bonding. Which way does the hydrogen go? It's known as the 6-vertex model. It's 6 of the 16 allowed arrow configurations. Some are disallowed. And there's a mapping, which well, maybe I'll just say it very quickly. From the T equals 0, Q equals 3 Potts antiferromagnet to the chromatic polynomial, okay? Or by duality, the proper 3 colorings of faces. So given such a coloring of faces, consider a square, let's say the middle one, 1. Pick a vertex VI, let's say that one, and the adjacent edge. So let's go in a counterclockwise direction. If the adjacent face has the next color cyclically, which is 2, the arrow goes out of that vertex, okay? Then you assign that arrow. Then you do the same thing here. Again, it's an arrow up. Here, it goes in. So now you go backwards cyclically, which is 3, and so forth. You continue this ad infinitum, and you thereby prove the correspondence between the vertex model and this ice model, and the Q equal 3 Potts antiferromagnet, or in other words, the chromatic polynomial on this lattice. This argument is due to Lenard. It was quoted in the paper by Lieb. This is the paper where he actually calculated the W for square ice, and it's shown here. And notice that this is very close to the experimental value. The correlation functions in the 6-vertex model are algebraic. It's massless. Therefore, we infer that the Q equals 3 Potts antiferromagnet is critical at T equals 0. There's a similar statement for Q equals 4 on the triangular lattice. And further work on that by Baxter. I don't have time to give this, but it's easy again to prove that there's maybe I'll just say it very quickly. You can easily prove the violation of the third law of thermodynamics. Take the coloring. So this is the thing. In other words, the chromatic polynomial makes a link with statistical mechanics in a very non-trivial and interesting way. Both things like properties of ice and violation of the third law. So consider a bipartite lattice. We'll compute a lower bound on P, choose one color for all vertices in G even, and then independently we can choose the colors assigned to each of the vertices on the odd lattice from the remaining Q minus 1 colors. We get this lower bound. We take the 1 over nth power, send n to infinity, and we get W, okay? Or S, in other words, is this 1/2 k log Q minus 1, which is non-zero if Q is greater than 2. Same method works on the triangular lattice, tripartite. Again, non-zero entropy if Q is greater than 3. So this is proof. These definitions I've given for a recursive family of graphs. The maximal region in the Q plane where you can analytically continue this W, I'll call region 1. And recursive family, in this case, the maximal point at which it crosses the real axis, I'll call Q sub C. Okay? And so now it's of interest to study these. For sufficiently large Q, P is positive, so we can just take that 1 over nth root and get W. There are regions in the Q plane where we can't do that because that's negative or complex. Then we can only determine the modulus. There's a further subtlety, which is that we have non-commuting limits. If we're approaching a particular Q sub S, and then we take that limit, then we take the limit n to infinity, that is not in general equal to the opposite. Let me give you a very simple example. Consider the chromatic polynomial for the free ladder graph. It's this. Now, consider taking n to infinity first and then q to 1. You get that, 1. Do the opposite, because that q minus 1 factor vanishes, you get 0. The limits don't commute. So we need to choose a particular order of limits, and this is ours. We take n to infinity first. This has the advantage of removing some discontinuities that would otherwise be present. The same thing applies for the free energy. Okay, so early studies of these, pioneering studies, were carried out by Biggs, Demerel, and Sands, Braha, Kahan, and Weiss, Baxter, Reed, and Royal, and many other people who studied real zeros. I'm really looking at complex zeros mainly here. if we consider a recursive family of graphs of some type S, for example, just consider a lattice strip of width Ly, length Lx, with some sort of boundary conditions, then the Potts and also Tutte polynomial has this BKW form. Coefficients, which depend on Q, times powers of these functions here, lambdas, they can be thought of as eigenvalues of some transfer matrix, raised to the power, which is the length, okay? And again, we can, the same kind of game, we play the same game of generalizing this to the complex plane and looking at where there are the switchings of these dominant eigenvalues. So I've said this before for complex temperature, so I won't belabor that here. And the situation here then is that we get several different kinds of accumulation sets depending on the type of graph. Tree graphs, here's the chromatic polynomial. B is just trivial because the only zero here that iterates is Q equals 1. Open chain of polygons, we get this chromatic polynomial. Here's the D function. And again, this has discrete zeros. The first interesting case is the circuit graph. Here's the chromatic polynomial. And if I now show what this looks like over here, we have this kind of region diagram in the Q-plane. So in the exterior of the unit disk, this term, Q minus 1, this lambda, is dominant. So that is the dominant lambda. The W function is Q minus 1. There's this boundary, non-analytic boundary, the accumulation set of the zeros, which, by the way, in this case, lie exactly on that boundary. And interior W magnitude is equal to 1. One can then ask the question, what do these sorts of things look like for larger strip widths? And we did that in a series of papers. For example, the next one we did was the with 2. The chromatic polynomials for cyclic immobiles had been calculated by Biggs, Emerald, and Sands, but we worked out the B for that. It's shown here. We have several interesting things. The QC is 2. It shows the regions, which lambdas are dominant, and there's a triple point here, and so forth. So we then continued this in a series of papers. Let me show you one continuation in one direction. We did homeomorphic expansions where we inserted degree 2 vertices on these upper and lower edges, okay? And again, there's an obvious generalization of the Biggs, Emerald, Sand type formula here, or with lambdas that are shown here. This was in a paper we wrote several years ago. And these lead to very interesting changes in the boundary locus B. For example, we can say exactly how many regions it separates the Q-plane into. It's 2k. And we can say in a very precise way, systematically, for any k, what's going on. This is what we find for one homeomorphic expansion, okay, where you get now these another bubble phase here. And we can do it for, notice here, there are 6 curves going through Q equals 2. For the other one, there were 2. When we go to the next even one, we go back to 2 again, and that pattern is general. And now we have another one of these phases. We generate just more and more and more of these phases. We have a complete control over this. So this is the type of family of graphs where you can completely specify what's going on out to arbitrary complexity. These are more difficult. These are sets of graphs we've looked at with various boundary conditions shown here: free, cylindrical, cyclic, Mobius, torus, Klein bottle. And we've generated a whole bunch of results. For example, this is for with 3, where we see some interesting features. Again, it has this general form. It crosses the real Q axis at 0, 2, 2.3. Notice this is marching up toward 3, and we we know what the dominant lambdas are for various regions. And we have this is what the actual chromatic polynomial looks like here. We have worked out how many lambdas there are for each d, where d is the degree of this coefficient polynomial. And this is an example of what is, for example, we have exact results for the this lambda here for any width, okay? Notice that some of these are algebraic non-polynomial functions. Of course, the chromatic polynomial is a polynomial. So what explains that? The theorem on symmetric polynomials in roots of algebraic equations tells us that although these, this is, for example, a square root, and we have cube roots in here and all that, but they only depend on the coefficients of the equations, which are polynomial. And that shows that even when you get horrendous results for the lambdas, you get, of course, as you must, a polynomial. And we've gone on to larger widths. This is y equals 4. You see QC is marching on up toward q equals 3. And this led us to a conjecture, which was that the limit was, in fact, 3. And we've done, this is, for example, 5, where again, this marches further on up. And in some magnificent calculations that Jesper will describe tomorrow, Jacobsen in Danish and Jacobsen in French have, and Jesus Salas have calculated these sort of things to higher widths, and agrees with this conjecture that QC should approach 3 as you get to higher widths. We've also, and again, I don't have time to show it, but it will be in the one in the transparencies on the web. You can do all sorts of interesting comparisons about how different parts of the boundary change when you change the width. Okay, but I have no time to do that. In the triangular case, it's also interesting. I'll skip a lot of the details, just show you one of our results. This is for width 5. We went from 2, 3, 4, 5. And here you see a number of crossings at various, if I can make this work, various values, and now it's 3.33, okay? So that's interesting in one direction. You can also look at free strips. Here you get very different types of structures. Arcs that in general do not separate the q-plane into different regions. Although when you go to larger widths, what happens is that the arcs elongate. The ends appear to come together, and it is plausible that these will actually, in the Ly goes to infinity limit, will come together at q equals 0. And I should say again that calculations for higher L have been done by Alan and Jesus and my work with Shichuan Zhang and so forth. Okay. We can also do something else, and this is, if you remember one picture from this conference on chromatic polynomials, this is the one you should remember, because this dates all the way back to Braha, Kahan, and Weiss. And we rediscovered it, but it is due to them. What they did was face coloring of honeycomb lattice, okay, which is, of course, equivalent to vertex coloring of triangular lattice with cylindrical boundary conditions. And this is in their paper given here, JCT 1979. So this is a sort of where the field kind of began. And as Alan beautifully pointed out in a footnote in one of his papers, the title of that article was, "Is the four-color theorem almost false?" Okay, because they had complex zeros that were coming right in toward 4. And of course, Gordon Royal sort of completed that for the real axis. Okay.
Actually, the title is the four-color conjecture almost?
You're right,
It's
of course.
actually very funny because it was published 3 years after.
Yeah, exactly. Yeah.
But if you look,
but Alan,
submitted before.
Exactly, that was the point.
It was submitted in 1975. And
right,
they never bothered to change
right,
the title.
right. They should have changed the time. So we've done
Beautiful
these.
title.
We've done these sorts of things on many other lattices. I won't bore you with it. This is the Archimedean 3-12-12 lattice. This is what it actually looks like. And various other Archimedean lattices, I won't show you those. We've also looked at cases where there's an attempt made to minimize finite size artifacts. And of course you do that by using doubly periodic boundary conditions, either toroidal or Klein-Bottle. And here I had the privilege of working with one of the very eminent people here. There are many eminent people here, but Norman Biggs. And we calculated Ly equals 3 strip of the square lattice with toroidal or Klein-Bottle boundary conditions. We got this. So I'm not going to say much about this because Norman is going to say a lot more about this tomorrow. But notice one interesting thing, that here, whereas the cyclic ones, we're just marching up toward q equals 3. Here we hit q equals 3 immediately, okay? The value for the infinite lattice. And we've done a whole bunch of other toroidal Klein-Bottle ones, but I'll skip all that and just say one thing, that in fact, for self-dual strips of the square lattice, you can get q equals 3 for each Ly you do, okay? So here's what we did for a it's Ly equals 1, very easy. This is for Ly equals 2. The Ly equals 1 is just a circle that goes through 3. It's the circle q minus 2 is equal to 1 magnitude. Here is q equals, is Ly equals 2. And again, you go right through q equals 3. And we did that for several larger widths. So this is, in a sense, a remarkable result. One has a family of graphs that incorporate a property of the two-dimensional square lattice, namely self-duality, which enables them, evidently, to always reach this maximal value of q sub c. And we've gone up to higher widths, but I won't show that. There are other interesting things. For example, with Jesus, we wrote a paper a while back on what happens when you go to higher dimension, above 2 dimensions. Here we go above q equals 3. We hit q equals 3.4 here. There's a lot more that can be done here also. This is simple cubic. You can do BCC, FCC, a lot of other interesting things. OK, so I'm sorry I'm going over time. I'll end very quickly now. Based on this, based on these various calculations, based on them and some other things, and we studied, as we said, of course, effects of graph topology, cyclic versus Möbius, where the lambdas are the same, Klein-Bottle versus torus, where Norman Biggs and I found that for the square lattice, there were 8 lambdas for the toroidal, but 5 for the Klein-Bottle. So very interesting difference. And Zhang and I extended that, and I think we more or less proved why that's true. OK, so at BCC 99 in University of Canterbury, I had put down a set of conjectures from what we have learned empirically, what might be true in general. One thing had to do with the dimensionality of B, and I'll skip this. It's really, let me just say that this is an interesting case, but when you go to complex temperature zeros, you have a very different situation. You can get not curves, but areas. In fact, we showed this for isotropic with Alan's kind of program of making the j's different on different, different edges. Here, jx is different from jy, okay? And I mean, it's all x's and all y, so it's not your full multivariate thing, but just a very, very small generalization. And here they generically form areas, not curves, okay? So the topology of B is of great interest. How many regions in the q-plane does it separate? Does it cross a real axis? How many components? What kind of singular points are there? There are all sorts of interesting questions, which in some sense are a mix of graph theory, complex analysis, and algebraic geometry, and topology, okay? We conjectured that and it ran out of battery too. Oh, okay. For a recursive family of graphs, a sufficient condition for Q to separate the Q-plane into different regions is that it contains one global circuit. Roughly speaking, periodic boundary conditions. That is not necessary. We know that from this famous BKW. It's Braha and Kane, actually, in JCT in 1979. So some more questions in algebraic geometry. Multiple points, intersection or T-type or Y-type points, arc endpoints, all sorts of interesting questions come in here. And Norman Biggs is going to give a very nice talk on this. And Alan and Jesus have worked on this kind of thing also. How many connected components are there? bounds from algebraic geometry, the Harnack theorem, are very weak here. For example, I didn't go through it, I don't have time, but in one case we generated a family of graphs where the Harnack bound gave 37 components. We got 2. Okay, so it's not, I mean, but we know the Harnack bound is sharp. Okay, so something can be done there. In general, there's a question as to whether the zeros actually lie on the asymptotic boundaries. In general, they don't. We answered this in the affirmative for, in fact, this is very easy to do for a certain class of generalized wheel graphs. How do W functions in region R1 compare for different boundary conditions? We conjectured that beyond Q sub C, they're the same. This has been proved in this paper. Another thing is this monotonicity of the W function as you're approaching the two-dimensional thermodynamic limit. Another thing is the compactness. Under what conditions are the chromatic zeros and their accumulation sets compact? We generated a whole bunch of special curves. Actually, Gordon Royal and Ronald Reed did this first. We generalized theirs, and this was further generalized in some beautiful work in these papers here by Allen and Jason Brown and Hickman and Dave Wagner. After that, we worked further on this, and I'll skip all this except to just mention, well, I should probably skip everything here. Okay, but anyway, some questions, okay? Is there a recursive family of graphs that always gets the asymptotic Q sub C? We answered that yes. We didn't really know that at BCC 99, but we answered it shortly thereafter. So that conjecture has been answered. And I'll skip the details of that, except just to mention that, among other things, the number of lambdas increases exponentially fast. So the higher order calculations get very, very difficult. How well do we understand the magnitudes of the zeros and, of course, the accumulation sets? So Allen has this beautiful theorem shown here, generalized by Fernandez and Procacci slightly with this C here. But for what we're doing, if we actually look at one of, if you remember what those things look like, they go out to around 3, 3.5, things like that. And yet, those are for degree 3 or 4. So, 7 times 3 is 21 for the triangular lattice. 7 times 4 is 28 for the square lattice. And for the triangular lattice, 7 times 6 is 42. So those bounds are way beyond what you actually get. However, as Allen has emphasized quite correctly, for a general graph, they're actually it's not clear they can be improved that much. So the idea is to use the specific properties of recursive families of strip graphs to get more restrictive results. So this motivates further study of SFP type upper bounds, taking into account specific properties of our graphs. Okay, so then let me conclude. I didn't have time to do this, but you can see it in what's on the net. You can do other slices of this hypersurface in 3 complex variables. You can study B in the Q-plane for fixed V away from V equals -1. We've done that to some extent. You can study B in the V-plane for arbitrary Q. It doesn't have to be an integer. You can take Q equals 3/2, whatever, and work out Fisher zeros for all sorts of Qs. Okay, so that's on the net. You can look at that. And finally then, conclusions. The zeros of Tutte and these Potts polynomials are of great interest. There's been a lot of progress. The study of the zeros in these sets connects all sorts of different fields. Combinatorics, graph theory, algebra, complex analysis, algebraic geometry. I've submitted some problems to the problem session, mainly on complex zeros, by the way, deliberately, because I know a lot of people are working on real zeros. And let me just say, this type of workshop is a superb place for physicists and mathematicians to get together and discuss these topics. So I certainly am very grateful to the organizers of this, and I hope there are a lot more of these in the future. Thank you.
Okay, we have time for 10 or 20 questions.
Well, I have one quick question.